Hello, 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 everybody, and thank you for joining me. We are on the very last question of the 2008 Euclid contest. It's question number 10. It's all written, as we would expect. And what have we got here? No A, B, and C's in sight. We have to scroll down for them. So there's 3 parts here. And what have we got? Suppose that n is a positive integer. Consider an upward pointing equilateral triangle of side length n cut up into unit triangles. Okay, just as we've got shown. So for n equals 3, so we've got, 1, 2, 3 along the sides. And you'll notice we have just trying to make connections as I read the question. I know when I cut up an equilateral triangle, just from experience like this, if the side length is n, there's actually going to be n squared of these unit triangles. I don't know if that's going to help. We'll find out. But you'll notice, if you count here, there's going to be 16 of them, because we got 1, 2, 3, 4 along the sides. All right. For each n, let Fn represent the total number of downward pointing equilateral triangles of all sizes. Okay, they got to be downward pointing. They do have to be equilateral triangles. And so, for example, f of 3 is 3. Why? Because we've got 1, 2, 3 of them here. And f of 4 is 6 for these individual ones here. And this one bigger one, because all sizes count. Okay. And so, if we were even bigger, you could get sort of one that was of size 3 and pointing down. That's the idea, probably for this f of 6 here. So A, determine the values of f5 and f6. Now for question 10, I usually, especially if they introduced a brand new concept, I usually try and read all 3 parts, just because it gives me a sense as to where they might be going. Because quite often with question number 10, they'll introduce a brand new concept. It's not like here's this really tricky quadrilateral inside a circle and you need to really, really know geometry to prove what we're asking you to prove. Often it's just... I find so questions like the weird quadrilateral inside the circle, and this angle and this angle prove that these 2 lengths are the same. A question like that is just, how much math have you studied? Okay, are you just an encyclopedia of circle proofs and weird facts about geometry and things like that, or other areas of math? But question 10 on the Euclid is not, how well do you remember all that math from obscure textbooks? Question 10 is very much, here's a brand new concept that we suspect that none of you have ever seen before. How quickly can you cope with it? How quickly can you develop theory and use logic and reasoning, which is the real core of what math is. You can get through high school probably by memorizing a lot of math, but to actually go on and do a degree in math at the university, or any university, you need to understand the finer points of logic and counterexamples and proofs and things like that. So being able to cope with a brand new concept and develop a formula, or develop, if it looks like this, then the only possibilities are this and this. That's sort of a theory. That's very good, and that's exactly what I like seeing on a question number 10. So being able to read all 3 parts gives me a little direction as to what sort of stuff I might be developing. So I can already see for B here, prove that f of 2k, so f of an even number, is f of the previous odd number plus k squared. So there's a formula. Should I develop a formula for an odd one as well? I mean, they're not asking me for that, but maybe I'll need that for C part. Okay, so, maybe f of 2k plus 1 in terms of f of 2k plus something. I don't even know if that can be done, but is that something I should be looking towards? Okay. C part, determine with justification all positive integers n for which fn is divisible by n. So maybe not so much a recursive formula, but maybe if I could get some sort of closed formula for n. Maybe fn is n cubed plus 2n squared. I have no idea what it would be. But maybe something like that. Or maybe, and I'm not going to keep just sort of shooting out ideas, but one last thought is, maybe it's fn looks like, I can get a closed formula if n is odd, and a different formula if n is even. And then, then I ask, well, which n's do divide fn? And then I assume n is odd, then I assume n is even, and yada, yada, yada. Okay? So those are ideas, but let's ease ourselves into the question by doing a part and just figuring out f of 5 and f of 6. Okay? That should still be worth a couple marks for us right there. Okay, so we'll go to our notepad. We want f of 5, so let's count these out. Now, if I'm just going to draw pictures, I'm going to do it in the same style that they did it, which is to say, 3, 4, 5. I'm just going to draw pictures of the ones that have just 1, and draw pictures of the ones that have just 2, or things of size 3. There we go. That's not bad. Got a few more I got to add in there. There we go. So what would I do if I just wanted to draw a picture? Well, okay, here purple is all the downward facing ones. Should be 2 more, but I forgot to add those lines in. But there we go. So that's 1, 2, 3, 4, 5, 6. So there's 10 of them here. Okay? And it might be a good idea to keep track of what numbers we've got here. Okay? So let's draw another one. I don't think we're going to get any size 3 ones this time. But next time, certainly. So for F6, we should be able to. All right, so now here's one. Here's another one. And here's another one. And those are really the only ones of size 3, or size 2. So I would say that there's 13. Okay? And we can look at this a little more closely, but I think we can very confidently decide there's really going to be only those 3. So I would say something like f of 5 is 13, and I move on. Let's draw some pictures for f of 6. Now, one thing that I might want to start doing here is just taking a look at how am I getting these new ones, and is there sort of a recursive way? Because I'm aware that B part has sort of this. If you do f of 2n, how does that relate to the previous one? Or I guess they had k. So I'm aware that I need to be interested in the relationship of how do I go from the triangle of size 4 to the triangle of size 5, or how do I go from the triangle of size 5 to the triangle of size 6? So here's a great little idea. We know that f of 5 is 13. We know what b is expecting of us, so the answer should now be plus 3 squared, so we should get 22. Can we see why there are 22? Okay, so let's get some pictures going for F6. So we'll need to split it in 3. 1, 2, 2, 3, 4, 5. There we go. Okay, so those two get connected together. So I'll just thicken these points up. I'm not drawing perfectly exact pictures, and I wouldn't recommend you do it either, or you're going to waste a lot of time. It's like when I see people on exams getting out a ruler when they're being asked to sketch a picture of a graph. No, just axes, and there's your 1 over x. Don't waste time on the niceties unless you need a very particular diagram or you're really obsessive. Okay, what I'm going to do here is I'm going to say there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. those are 10 that come from F5. They're in the first 5 rows. And then we've got 1, 2, 3, 4, 5 new ones that are singles. Now this time we're actually going to have a downward facing one of size 3. So we got to be prepared for that. Okay. Just fill in some of these dots so I don't think that they're smaller triangles trying to get away. So we'll have one brand new one over here at the end, and that's this big one in the middle, 3. Okay, now, but what about the size 2s? Well, we have a few size 2s in the first 5 rows coming from F5. Okay, we have 3 of them. And then we have a few new ones. And those new ones we're interested in. Where do they come from? How do we know how many of them there are? Okay, so let's get the orange out. There's 1, there's 2, there's 3 of them. Now, what about new ones? And let's consider our brand new row that we've got. So, in terms of a downward facing triangle, it's gotta have sort of a peak down at the bottom. Now, if that peak appears in any of the previous rows, this bottommost peak, and so I'm starting to form my argument for B, then it's already counted by F5. So we consider we've got these 5 pieces down here. Could any of them be a peak for something, for a triangle of size 2 or eventually a triangle of size 3? Well, these 2 off on the side are no's, but we do get 3 new ones as we move further in. So we have the 3 from F5, and then we've got 3 more here. We've also got 5 more here and 1 more here. Well, there's your 9. There's 9. There's 3 squared being added. And we can even... So there's 1 here, there's 6 here, and there's 15 here. And so that adds up to 22. Another thing I'm noticing, and this is just because I'm quite comfortable with numbers, I've been doing these contests a lot, I'm noticing that these numbers here are special. They're actually called triangular numbers. And the ones that we had previously, 10 and 3, these are triangular numbers. And the triangular numbers, if you're not familiar with them, they start out with 1, then 3. They are just natural numbers who can be represented as, well, the number of triangles that we... the number can be represented as a triangle in terms of... the number of... If I have that number of dots, they can be arranged in a triangle, is what I'm saying. The next one's 21, and then 28. They all have a nice little form. It's n times n plus 1 all over 2 is the nth triangular number. Okay, and I'm noticing that these are here. Okay, so 13 is 3 and 10. The 22 that I just got is 1, 6, and 15. I'm betting the next one is 3, 10, plus 21. And then f of 8 would be 1 plus 6 plus 15 plus 28. I could check these things. I'm also noticing f of 4 was 1 plus 6, and f of 3 is just 3 by itself. And f of 2 is just likely 1. Let's double check that. Yeah, it's just 1. And f of 1 is, well, there's nothing. So this is another pattern, and I don't know which one I'm going to go with. Certainly I'm going to use sort of this, does the peak of, or does the trough, or the bottommost point of a downward triangle, does it lie in the first n rows, or is it in the n plus first row that I just added on? I'm going to use that to prove the recursive formula in B part, because we are done A. But I am making the connections with these other numbers. Okay? We might even claim that, there's this triangular many numbers that are single triangles, there's this many size 2 triangles, there's this many size 3 triangles, and get a formula that way. Well, we'll see. We'll see. Okay. We need to do B. So, we got to write something up. Consider a triangle of size 2. It's 2K. Okay. And suppose we wish to calculate f of 2k. Well, we do. We do wish to calculate f of 2k. Let's count the triangles of, let's say, size, we've used k, so let's say m. Okay. This triangle of size m is facing down, because that's what we're counting. Yeah, so there's an example. So this triangle is facing down. Consider its lowest triangle. And I draw a little picture there. Okay, so the lowest triangle. What row is this lowest triangle in? If it is in the first 2n minus k rows, it is the same as a triangle in the big triangle of, let's say, size 2k minus 1. And you might want to draw a little picture. So here's our bottom row. And so here's this triangle. Let's say it's this one here. Okay. So it is counted by f of 2k minus 1. So either the triangle I'm looking at is in the first 2k minus 1 rows, or it's a brand new triangle that comes from our newly added 2nth row, the next row. So otherwise, the lowest triangle is one of the 2n minus 1 in the bottom row. Okay. So, now, what do we want to say? So let me draw a picture of a bottom row here. Do I have an even number? 2, 4, say, we'll do one more. Okay, there I have an even number. Now, if this lowest triangle is the bottom of a size M triangle, then, so I can't put, so not all of these bottom triangles here in purple, just to explain to you what I'm doing. Not all of these could be bottoms for size 2 triangles. For example, these ones over here on the corners, they can't be because we're outside the whole triangle. Just like the ones that are within 2 of the side can't be bottoms to triangles of size 3 or 4 or something like that. So as we go in, each of these single triangles can be the bottoms for how many triangles? Okay. And I need to find a way to explain this or to justify this, to reason this. Otherwise, I likely won't get full marks. Okay, so if this triangle is the bottom of a size M triangle, then I want to say something about how it doesn't go outside or it isn't out of bounds or anything like that. Or should I say this another way? I'll say it this way. So for each of the 2n bottom row triangles is the is the lowest triangle for a triangle. I'll make them downward facing here. For a downward facing triangle of size 1. Okay. All but the outer 2 are lowest triangles, trying to use the same sort of terminology. Are lowest triangles for a downward facing triangle of size 2. And here's where I would draw my picture of you don't want to go outside. Otherwise, the triangle lies outside the big triangle. We're using the word triangle a lot. You might want to define terminology like the big triangle, a downward-facing triangle, a lowest triangle, a single triangle, a peak triangle, those sorts of things. Okay. As we move inward along the bottom row, less triangles. In fact, 2n minus 1 minus 2 times m minus 1 can be used as lowest triangles of downward facing triangles of size m. Okay, so what have we got? So we've got 2n minus 1 of size 1. We've got 2n minus 1 minus 2 of size 2. We've got 2n minus 1 minus 4 of size 3, all the way down to 2n minus 1 minus... And so here's the real question. What's the most we can have? 2n minus 1, I think. Of size n. Yeah, because for 6, the biggest we had was something of size 3, which is half, because we're looking at a big triangle of size 2n. So now what I need to do is add all these up. So this is 2n minus 1, this is 2n minus 3, this is 2n minus 5, all the way down to just plain old 1. Right? Is it 1 or is it... Yeah, it's just one of them. Yeah. Alright, so what I need to do is add them up. So f of 2k, I've been using n's the whole time, haven't I? Change these. It's going to be boring for about 2 minutes now, as I change my n's to my k's because I got to use the right terms. Otherwise the marker's going to say, where the heck did n come from? I thought we were talking about k. Alright, there we go. We're back to the k's. Alright, so now I need to add these. So f of 2k is the ones coming from... So here, I'll just remind them lowest triangle is in the first 2k minus 1 rows. Plus, and now 2k minus 1 plus 2k minus 3 plus all the way down to plus 1. So the question is, well, what is the sum of all these odd numbers here? And it had best be it should be k squared, but how do we explain this? What do I want to use a formula? So I'm going to say this is plus 2k plus 2k minus 1 plus 2k minus 2. Oh, no, sorry. It's k plus k minus 1. Plus k minus 2 plus k minus... No, k minus 1 plus k minus 2. Plus k minus 2 plus k minus 3. All the way down to plus 3 plus 2 plus 2 plus 1. And this is k squared. I'm trying to avoid having to use some sort of summation notation or something like that. But I think I'm going to have to. I really didn't want to, but yeah, I think it's probably just easiest to claim that this is... So I'll say it's f of 2k minus 1 plus k squared. And then I'll put a little star. And then off on the side I would do my little star proof. 2k minus 1 plus 2k minus 3 plus all the way down to plus 1 equals k squared. And we're going to do a quick proof by induction. Unless you're confident that they're going to recognize that this formula is actually k squared. And, maybe there isn't a mark assigned to that. I don't know the marking scheme, but if you're unsure, if you're worried that it is worth a mark, explain it. So proof by induction, this works if k equals 1. 1 is equal to 1 squared. Okay. Now, assume it's true, so... Assume this, then add on the next odd number to both sides. But, oh, look at that, that's k plus 1 squared. Proof by induction, okay, very quick, it's over. It doesn't have to be quick and strenuous like that. If it's worth a mark, there you've proved it, you've earned your mark. I'm not entirely convinced it is worth a mark. I think the mark is more for the explanation. But the explanation of, okay, there's this many of size 2, there's this many of size 3, and I got a nice little formula for that. Okay. So C part, just to remind ourselves what's going on with C part, determine with justification all positive integers n for which fn is divisible by n. Now we can already see there is one that does that. Its f of 3 is 3. Are there more? And do I want to get some sort of formula for fn? Can I get some sort of formula for fn? So, I don't know whether or not to go with B part and try and get a formula for 2... I keep saying f of n. I'm probably going to continue to say f of n, but I should say f of k. Can I get some sort of formula for f of 2k plus 1? And if so, should I? That's the real question. Should I do that? And I don't know if that'll be helpful. I think... So here's something I think. I think f of k is the... I don't know exactly how I want to say this. So, nth triangular number. And by the way, people marking know what triangular numbers are. So this is true. Now, f of 2. Okay, so f of 1 is 0. So technically, this is true. So, but I think this is just going to be some weird case. So, if... Oh, see, no, they use n here. So I'm going to keep using n. All right. So, and so I should probably change this to the kth triangular number. Letters are fun. So if n equals 1, then yes, we're good to go. Now, f of 2, I've already marked it's 1. F of 3 is 3. F of 4, they were kind enough to point out, is 6 plus 1. F of 5 is 10 plus 3. Plus 0, and I guess this should be plus 0. And technically it's the 0th natural number. F of 6 is 15, which is not... so that's the fifth natural... The fifth... Yeah, we start with the fifth, and then we add on the third triangular number, and then add on the first triangular number. So I think f of n... So here's my claim. This is what I think. I claim f of n equals n minus first triangular number plus the n minus third triangular number plus the n minus fifth triangular number plus all the way down to, it's either going to be plus 1 if n is even, or plus 0 if n is odd. Or I guess you could say 3 because the 0 doesn't really matter, but I am trying to include f of 1 here. Okay, and this one's 0, this is 1, this is 3, this is 7, this is 13, this is 22. So far, only 3 has worked, and maybe 3 is the only one, but I have to prove that. Out of curiosity, if this is true, and if I think my claim is true and I'm going to use it, I would have to prove it. But if it is true, what would f of 7 be? The sixth triangular number is 21. So 21 plus 10 plus 3 plus 0, and that's going to be 34. So that one doesn't work. How about f of 8? And after that, I think the first two are the only two that'll work. But that'll be 28 plus 15 plus 6 plus 1. So that'll be 22 plus 28. That'll be 50. No, 8 isn't a factor of that either. So it really looks like n equals 1 and n equals 3 are the only two that work. But I would need to prove that. I also need to prove that this formula is, in fact, correct. what to do. So I don't think it'll be that hard to prove this formula correct, because I think what's happening here is this is counting the number of size 1s. Here we're counting the number of size 2s, the number of size 3s, the number of size 4s in my triangle. And just as a quick little double check, you'll notice the difference here is 16, which is half of 8 squared. So that really lends some believability to my claim. I would need to prove it, but before I go ahead and prove it, let's see if we can muck about with it for a second and see if this will show why. Like, can I even get a closed form? That's what I'm really worried about. Can I get just an expression for f of n, with n being odd or n being even? And I'm not entirely convinced that I can. Maybe I can, but So here's another claim. So here's another observation I could make. Based on if that formula is true, then I don't think it's going to be very hard to prove that f of, let's say, r plus 2 is f of r plus the r minus first. Sorry, the r plus first triangular number. Okay, so that's not so bad to show, because f of 5 is just 10, which is the fourth triangular number, plus f of 3. So not weird, but again, how would this help me? How would this show anything? Well, r plus 2 divides f of r plus 2. Well, actually, here we go. So no. Let's stick with that. R plus 2 divides f of r plus 2, which is f of r plus r plus 1, r plus 2 over 2. Now, I do note that if r plus 1 is even, then r plus 2 divides r plus 1 over 2, because that's going to be an integer times r plus 2. And that would then imply that r plus 2 needs to divide f of r. So, that's something, but of course you're making the assumption r plus 1 is even. And so, then that of course implies r is odd. And then you'd have to ask, okay, but what if r is even? Does it work at all? What to do? Because this doesn't show me any value. This just sort of passes the buck to, is f of r a factor of r plus 2? So is there any other pattern I can notice here? Well, speaking of odds and evens, what's going on here? So we've got even, odd, 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 even, even, even. By the way, while I'm not going to prove this claim until I actually use it for something, I am going to continue to assume it's true, because I think it's pretty clearly true. Let's get a bigger chart. So I'm going to write some of my triangular numbers, starting with 0, up here, just so I can work with them. We are very much in the investigation phase. Now, you want to investigate for a period of time. If you don't quite know the answer, the next one will be 45 and then 55. So you want to investigate for a period of time, but you don't want to over-investigate and then you don't have enough time to write up any of the little things that you do find. Like, I think that claim of that other formula is good enough. I think it will lead somewhere. I just don't know where. So let's get n and then f of n down here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The next triangular number, by the way, is 66. I'm just adding up the first so many natural numbers. But it was 0, 1, 3, 7. And then we add on 10, which is 13. Add on 15, which is 22. Add on 21, which is 34. Add on 28, so that's 50. Add on 36, so this one will be 70. Add on 45, so that'll be 95. Add on 55, so this will be 125. Add on 66, so that will be a 1. Carry the 1 is 10, so that'll be 161. The next one is 78, so add on 78 here. 3, carry the 1. 8 is 7 and 1, so we'll get 203. I'll just grab my calculator really quickly. I'm pretty sure 203 is not a multiple of 13. It is not. Okay, so it's really, really looking like the only two that do work are n is 1 and n is 3. But being aware of that, while a good thing to write down and a good guess may be worth a mark, it's not a proof, and we need to prove this. So, what can we do? Not noticing anything better in the numbers, although I am filling out my values a lot faster. But, it's entirely possible that I am going about this the wrong way. Now, what if we were to use b as our inspiration and say, well, if n is odd, so if n maybe looks like 2r, then I know it's 2r minus 1 plus, what do we want to say here? R, so 2r plus 2r minus 1 times 2r all over 2. And so that would be equal to f of 2r minus 1 plus divide by 2, so that would be 2r minus 2. So that would be 2r squared minus r. Yes? I feel like that's right. Okay. So you definitely have the factor of r sticking around there. And now, what if it's odd? Well, that's f of 2r minus 1 plus 2r times 2r plus 1 all over 2. So that'll be f of 2r minus 1 plus 2r squared plus r. Very, very similar looking formulas here. It's just really the plus or minus r that does something to it. But again, I'm not seeing how this will relate to showing whether or not n divides Fn. So I think perhaps I'm going about this the wrong way, although I'm not yet seeing the right way. And that is, of course, always the challenge. Okay, new tactic. Instead of using a recursive formula, I'll say f of n is, it's n minus 1 times n over 2 plus n minus 3 times n minus 2 over 2. So this is not so bad. n minus 5 times n minus 4 over 2. So I'm using that formula. I haven't proved it yet. I haven't proved my claim of what the formula is. We will get to that if we need to. But really, we are investigating. This is all work being done on a scrap piece of paper. So all the way down to, well, it really depends on whether or not it's odd or even. So it'll be either 2 times 1 over 2, or sorry, 1 times 2 if I'm writing it the same way that I was. So 1 times 2 if n is odd. No, if n is even. Yeah, if n is even. Because the second number is the even number, and n is the second number over here. So if n is even, or 0 times 1 over 2 if n is odd. So there's this, and so I guess I could write I could get it all over 2. Is this going to help in any way? Well, we could expand it out. N squared minus n. We'll get n squared minus 5n plus 6. N squared minus 9n plus 20. So how many n squareds will I have? Oh, okay. So n will divide Fn, so I don't need to worry about the n squareds. They don't matter, because of course they're divisible by n. I don't need to worry about the minus n's. They don't matter. So it's these numbers 0, 6, 20. The next one will be 6 times 7, so 42. Does n divide these? That's what I need to worry about. I think. Yeah. Okay, so the question is which n's, and how do I to figure out how far do I go here, and what are these numbers? 0, 6, 20. So, well, this is 0 times 1 plus 2 times 3 plus 4 times 5 plus 6 times 7 plus 8 times 9. But how far do I go? Well, I'll need n over 2 of them. Do I use floor function or do I use ceiling function? It's roughly n over 2 of them. And well, I think the only way to do it is to actually write a few of these out. So f of 3, for example, is 3 times 2 over 2. And of course, it's all over 2 as well. 3 times 2 over 2 plus 1 times 0 over 2. So we had 2 of them. We have 2 of these. Okay. 3 minus 0 times 3 minus 1 plus 3 minus 2 times 3 minus 3. We go until we hit 3 minus 3. Or 3 minus 2. So that's 3 squared minus 3 plus 0. And that's 3 squared minus 5 times 3 plus 6. So I had 2 terms there with 3. So 3 gave me 2 terms. And this will all be divided by 2. So it'll actually be 0 plus 3. Oh, what a shock. We got the same. Yeah, I know. But so f of 4 is 4 minus 0. I feel like perhaps I actually don't think I've realized anything new. I thought for a moment I had. I genuinely don't think I have anymore because I'm just going to get the same numbers. So the question is still, does n divide this sum? Although it's 0 here again, and 3. So that's 4 squared minus 4 plus 0. 4 squared minus 5 times 4 plus 6. So 4 also gave us 2 terms. So we want to use n over 2 ceiling function. Okay, so that's how many terms of the 0, 6, and whatever. And it'll all be over 2. So 4 obviously divides all of this over 2. Does the 2 matter? I feel like the 2 maybe mattered. But then 4 needs to divide 0 plus 3, which it doesn't. Alright, I'm skirting around an idea. I think it may be true. Alright, so let's start proving my claim, and by the time I'm done my claim, hopefully I will be able to articulate my thought, because I think So now I'm wondering whether or not my thought will fully crystallize. Anyways, I think we should use this formula, so let's prove my claim. So here I'm actually writing something that I would write up for question 10 here. Okay. So I claim that f of n is n times n minus 1, and then n minus 2 times n minus 3, all the way down to, and this will all be over 2. And then it's going to be either 1 times 0 or 2 times 1, depending if n is odd or if n is even. Alright, now can I prove this? And if so, how? Actually, let's try for something that's easier and more visual. So for n, fn is n times n minus 1 over 2, size 1 downward triangles. I know it's been a while since we've been talking about this. I've mostly been mucking about with formulas. plus n minus 2, n minus 3. But maybe going back and looking at some of the geometry. Size 2 downward triangles plus all the way down to plus either 2 times 1 or let's say 3 times 2. Size, what's my size there? Size n over 2 triangles. All right, so how am I going to show this? Well, for that's just a bad triangle. Oh, I'm getting burnt out on this question because I do not have a clue right now, and it is a shame when that happens, and it's even worse when it actually happens on a real contest. I have had burnt out when I've actually written a contest back in the day. Don't write them so much nowadays. And it sucks because you know you have so much time and you're stuck and you aren't using your time properly, and it is absolutely frustrating. So one thing you can do is take a break and check some of your previous answers, make sure they're right. Although I admit you really have the drive to not do that because you're thinking, well, I'm going to be wasting time. Something's gone wrong with this picture. Oh, I'm so burnt out on this question. Alright. No, not doing it this way. Not doing it this way. Okay. I thought I could do it. Not going to do it. So what I'm going to do is instead... so I claim if n is even... then Fn is Fn minus 1 plus n over 2 squared. This was done by B part. Okay, this is exactly what B says. If n is odd, Fn is Fn minus 1 plus something that I'm about to figure out. So we do the exact same reasoning that we did before. 1, 2, 3, 4, 5... 6. I need another row. 7. One, two, three. That's a big row. 4. Let's shorten this up a little bit. I was drawing great pictures before. What happened to me? What happened? One, 2, 3, 4, 5 rows. So now we're looking at something odd. Alright, fine. There we go. We're good and done. So now, so it'll be if the bottommost triangle is in the first n minus 1 rows, then it's already counted by f of n minus 1. That's fine. But what happens if we're one of these bottom triangles? So just going back to part B, and I think even doing this, even if we have no idea how to actually answer C, will get us some marks. So the bottom n minus 1 triangles in the nth row are the lowest triangles for triangles of size 1. All but the outer 2 are lowest triangles for triangles of size 2. Yada, yada, yada. All but the middle 2 are bottom triangles or lowest triangles for triangles of size. So what's the biggest size we can have here? Looks like size 2 is the biggest we can have for F5, so size n over, well, since I know n is odd, it's going to have to be n minus 1 over 2. So this is going to be 2 times 1 plus, well, no, how many triangles of size 1 are there? There's n minus 1 of them. How many triangles of size 2 do we now have? N minus 3 plus n minus, what is it, n minus 5 here, plus all the way down to, it's going to be 2 instead. So if I divide by 2 on both sides, no, I don't want to divide by 2. I want to, this will be n minus 1 squared. So shifting it to get even numbers each time, it'll be plus n minus 1 over 2, I think. Alright, so f of n is f of n minus 1 plus n minus 1 plus n minus 3 plus all the way down to 2. But that's really f of n minus 1. And so that'll be n minus 2, which is odd, plus n minus 4, which is odd, all the way down to plus 1. Plus, how many of these are there? N minus 1 over 2 of them. And that'll be, we proved this by induction, this will be n minus 1 over 2 squared. And we can do a quick little double check. F of 3 is f of 2, which is 1, plus 2 minus 1 over 2, wait, sorry, 3 minus 1 over 2 squared plus 3 minus 1 over 2. 1 squared plus 1. And it is 1 plus 1 plus 1. F of 5, we know that that's 13, and that's f of 4 plus 2 squared plus 2, and indeed it is. It's f of 4 was 7, and it's plus 6, which was 13. Okay, awesome. So, what have I shown? So using B and this claim that I've just made, f of n is f of n minus 1, well, yeah. And then it's plus n over 2 squared, if n is even, n minus 1 over 2 squared plus n minus 1 over 2 if n is odd. Okay. That tells me f of n is, and I'm going to write this f of n minus 2 here, plus, and it's going to be either n minus 1 over 2 squared plus n minus 1 over 2 plus n minus 1 over 2 squared if n is odd. So this is coming from the n minus 1 is even. And this is coming from the n is odd part. Or if n started off even, then you'll have n over 2 squared plus n minus 2 over 2 squared plus n minus 2 over 2. If n is even. So there's coming from the even part, and there's coming from n minus 1 is odd. So we would subtract 1 as well. Oh, this is getting confusing, and I'm sure this video is becoming hard to follow, but if you want to read professionally done solutions that don't explain what they're thinking, that's what the Waterloo solutions are for. You can get the second link in the description takes you to their website. They have very clean solutions, and they're not hard to read, but part of what I do with these videos is I try and explain the thought process, what connections I'm making, or in this case, what lack of connections I'm making. Alright, so I'm going to clean this up, and hopefully I will finally get the formula that I want, which is n times n minus 1 over 2. Okay, so this is n minus 1 times n minus 1 plus 1. Okay, let's say it this way. This is 2 copies of n minus 1 squared over 4 plus n minus 1 over 2. But that's just, so canceling those out, that's just n minus 1 times n minus 1 plus 1 all over 2, which is just n minus 1 times n all over 2. Now this bottom one is n squared over 4 plus n minus 2 squared over 4 plus n minus 2 over 2. Somehow I want to make that n times n minus 1. Okay, so that'll be n squared plus n squared minus 4n plus 4 all over 4 plus 2n minus 4. It's multiplying top and bottom by 2. So these 4's cancel out. We'll get n squared minus 2n, which will be n times n minus 1. All over 2, because we divide top and bottom by 2. Okay, great. So I didn't have to prove this geometrically, because my picture drawing was becoming a bit of a nightmare. But here's a nice big statement. F of n is n times n minus 1 all over 2 plus f of n minus 2. I have it. I did it. It's there. It's done. So I have proven that ultimate sort of claim. Now, what can we do from here? So it follows that Fn is n times n minus 1 over 2 plus n minus 2 over n minus 3 all over 2 plus all the way down to either 2 times 1 over 2 if n is even, or 3 times 2. We'll say 1 times 0 over 2 if n is odd. Okay. So Fn is equal to n squared minus n plus 0 plus n squared minus 5n plus 6 plus n squared minus 9n plus 20. I'll deal with the even odd after this one comment, but we claim n divides Fn if and only if n divides 0 plus 6 plus 20 all over 2 plus n over 2 floor. No, it was ceiling. It was ceiling, wasn't it? Yeah. Okay, so it goes 0, 1, 2, 3, 4, 5. N times, and it'll be either +1 or -1 depending on whether n is odd. There we go. That'll do it. So it'll be if n is 3, then this would be times 0. Oh, why am I having so much trouble with these formulas? It's n plus 1. So I'll say that's what it is. All over 2. Okay. So, indeed, so let's prove this. N divides we're going to have to write a big formula here. So, here we go. Fn is going to be, well, how many n squareds would there be? There would be n over 2 ceiling function n squareds. We talked about this 3 over 2, there were 2 n squareds. And for 4, there were 2 n squareds as well. Plus 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. So, well, minus actually. Minus some number of n's. I'm going to verify, I'm going to sort of fact check this in a moment. Plus 0 plus 6 plus all the way up to plus n times n plus -1 to the n plus 1. I would like to also... Gotta be careful when I draw my lines. I would like to also comment that this is taking so long, I feel like there should be a faster way to do this question, and I would love to see what their solution is. But as a rule, I don't look those up while I'm writing up my own solutions. So I've got what I claim is my formula. Let's just double check this. What is f of 3 and what was f of 4? Okay, we had n squared minus n plus 0, n squared minus 5n plus 6. And for this one, we had n squared. So 3 squared and 4 squared. I do not want to even imagine what the time on this video is right now. 4 squared minus 4 plus 0. Plus 4 squared minus 5 times 4 plus 6. Again, all over 2. Let's just grab our calculators quickly and confirm these numbers are correct. 9 plus 9 minus 3 minus 15 plus 6 all over 2. Yep, that's 3. 16 plus 16 minus 4 minus 20 plus 6 divided by 2 is 7. Okay, good. I do have n over 2 ceiling functioned 3 squareds and 4 squareds. N over 2 in this case is 2 times 2 plus 1 all over 2. 2 times 3 over 2. So it's not right. So that's not right. But it is. It's minus 0, minus 1, minus 2, minus 3. And minus 0, minus 1, minus 2, minus 3. So I need... And then the next ones would be minus 4, minus 5 for f of 5. So I need n times n plus... Well, it'll be plus or minus 1 depending on what factorial we're looking at. Right? So if it's 4, I want to do 3 times 4 all over 2 to get 6. If it's 3, I want to do 3 times 4 all over 2 to get 6. So I want n, and then it'll be n minus 1 if n is odd. Or sorry, if n is even. So there we go. Okay. And then I had 0 plus 6 and 0 plus 6. And the next one would be 20. And then that would be 4 times 5. Something's wrong with this end formula here. Because when I plug in 4, I get 4 times 3, and that's not 6. So I think it needs to be n minus 1 n minus 1 and then n minus 2 plus negative 1 to the n plus 1. So if I plug in 3 there, I'll get 2 times... No, that's not working. So we'll say n minus 2 and then n minus 2 plus... Yeah, there we go, there we go. Plus n minus 2, and then n minus 2 plus negative 1 to the n. So this will be... Do I need 1. 1 here, 1 here. So this will be 2, and I want to make this times 3, so it'll need to be plus a 1 if n is odd. So it'll be n plus 1 is then even, and this will be negative 1 to an even, so it's plus 1. If n is 4, this is 3 times 3 minus 1, which is 2. Okay, good, good, good. Formulas are all working out. Okay, I don't need to justify this as long as it's correct, so let's just erase my little extra work here. And if I'm not onto the right track, I think this might end up being my first 2-hour video, and that would be just awful. Just awful, but sometimes that's what happens. Sometimes you just can't do a question. But anyway, let's see here. So I claim that obviously... So I claim that only this last part matters. Also, I need to go back and correct my formula. N minus 1, and then when it's... There we go. Alright, so I need that. I don't even know how I'm going to argue it down past that point. So that'll be something for me to consider. So I can take out a factor of n here. I just feel absolutely stuck at this point because I can definitely, obviously, no matter what 2 is, so this is n times, I want to show that this part is always an integer. When I divide by 2. And that might not be the easiest thing in the world to do. I'm genuinely tempted. It's been so long, I feel like maybe I need a fresh start because these formulas are becoming too ugly, I would say. They're a little unmanageable, and I'm not liking that. I'm not saying it's impossible to continue on from here. I'm just saying I'm really not liking this. It's always hard to do. I don't think a 10 has gotten me this bad in any of my past videos. That said, I've said in the past that a video is like an hour and a half long, and it turns out it was 40 minutes, and I was just psyching myself out in my head. But when you're stuck on a contest, and I do try and treat these as though they're contests, I don't get outside help. Like I don't have a phone lying around to try and do these or anything like that, or a graphing calculator to help me graph. So I try and treat it like a contest, and so I'm reaching that critical point of, do I keep slogging away with formulas that, and you're watching me have trouble like figure out what the formula is, or do I go back to the basics and try something else? Like, I have noticed a pattern, and that pattern has led me to these formulas here. But I'm struggling to put them together, and I'm at a point where I'm sort of stuck as to where to go and to show. Because even if I do manage to show that n factors out and that what I'm left with is 0 plus 6 plus 20, how am I going to show that only 1 and 3 work with that? That's the real challenge there at that point. So I think... honestly, I'm just mucking about here. So I think I need to just go back for a second, take a look at the problem, maybe and make it a little cleaner. Like, yes, I noticed a pattern. Was it the right pattern? It doesn't look like it was. Now, they tell me about recursion in B part, so should I be using recursion? And this is not to say that I have to throw out everything I've learned. I did learn that recursion that Fn is Fn minus 2 plus n times n minus 1 over 2. That's a nice solid recursion because this works regardless of whether or not n is even. But in B part, they very clearly have an even number. So should I break it up? As I had, the reasoning's there. I did prove a claim with it. Or I don't know what to do here. Maybe recursion isn't even the right way to go. Maybe there is a way to get a closed form solution. Like I'm suspect that it would be a different, like, you know, notice here the difference is a square, so it would probably be a cube if it's going to be anything. But maybe there is a closed form that I can do something with, and you know, that's just crazy enough that it might be a good idea. So let's see what we can see. Okay, so what do we want to do? I'm happy that I have proven this. I'm not taking that away at all, because I did do the exact same argument with CPART, but let's suppose it's even. So then that tells me I've got f of 2k minus 2 plus, it'll be 2k minus 1 all over 2. So if I called this g of k, and then this would be g of k minus 1, we have this formula. I can divide by 2 on both sides here. So you might want to say off to the side, if you're introducing a new formula, tell them what it is. So, you know, this is nice and true, but is this going to lead me anywhere? And if so, where? So if I rearrange this, I could say something like, (2k squared minus k). So first differences are quadratic. G of k is a cubic. And so, okay, let's just make it a generic cubic. Man, I don't think this is the most elegant thing that I'm doing, but it's getting me closer to maybe a closed form. So I want to write that. That's a k minus 1 cubed plus b k minus 1 squared plus c k minus 1 plus d plus 2k squared minus k. Alright, that was the correct formula. Yeah, 2k squared minus k. Alright, so that'll be a k cubed minus 3ak squared plus 3ak minus a plus bk squared minus 2bk plus b plus ck minus c plus d plus 2k squared minus k. Alright, let's get to canceling a few things out. AK squareds, BK squareds, CKs, Ds. So comparing coefficients, we know 0 is going to be, I'm going to divide everything by -1 just so I have a positive leading term. So there's my only k squareds. Oh, no. Never mind. I'd have more than just that. So I'll keep it as is. 2 minus 3a k squared plus 3a minus 2b minus 1k plus -a plus b minus c. And it doesn't look like anyone cares about what the d is. We'll figure out the d later. We know f of 2 is 1. So that'll help us out. So 0 has got to be 2 minus 3a. 0 has got to be the same as 3a minus 2b minus 1. Well, this first one tells me a is 2/3. And then so that's 2 minus 2b minus 1. So that's 1 minus 2b. So b is 1/2. And then 0 is going to be negative 2/3 plus 1/2 minus c. So that'll be c is equal to 1/6. So what have we got? We've got 2/3 k cubed plus 1/2 k squared plus 1/6 k plus d. We know that g of 1 is 1 because that's what g of 2 is, or f of 2 is. And so that'll be 2/3 plus 1/2 plus 1/6. 2/3. So 1/2 plus 1/6 is 2/3. 2/3 plus 2/3. So d must be minus 4/3. So that tells me g of k is, put everything over 6. So that'll be 4 times k cubed plus 3k squared plus k minus 8. Yikes. Okay. Is there anything I can do there? Oh, you know what? It's not supposed to be 0, so this should be minus 1/3. Oh, I'm glad I caught that. That could have been a disaster. So this will be minus 2. That still doesn't particularly help me. I feel like maybe I could factor this and then ask whether or not 2k divides this. Is there anything that really sticks out in terms of... So if I put in 0, I don't get 0. If I put in negative 1, I'll get negative 4 plus 3 minus 1 minus 2. So that didn't work. Just to be clear, g of 2 should be f of 4, which would be 7. Do I get 7 here? So that would be 32 plus 12 plus 2 minus 2. 32 plus 12 is 44, which is not divisible by 6. Something has gone wrong. Something has gone hinky. What did I screw up this time? Oh, I'm so done with this question. I'm really not liking this question. So those 2's cancel out. 32 plus 12 is 44. I want it to be 42. So, oops. Something's gone wrong. Is one of these numbers supposed to be negative and I don't know it? I think C is negative 1/6, and then that would change this. So we'd get a half minus a sixth is a third, and looks like there's no D value. And so that would actually make, so that would make it 44 minus K is 2, so that'd be 42. So, okay, there we go. And this makes it much, much easier to factor. I'm loving that. So we'll get 4K squared plus 3K minus 1. I feel like there's a 4K, maybe a minus 1 involved. And then, oh no, it should be minus 1 here, plus 1, I'm thinking. So if I plug in 1, I get 0 out. That's not good. Because if I plug in 1, I should get 6 out. Yeah. No, that should go to 1. If I plug in minus 1, I get minus 4 plus 3 plus 1. Good, good, good. All right, that all over 6. Okay, great. So I managed to get a closed form. So that's what f of 2k looks like. And that's wonderful. I love it. Can I do the same thing to if it's odd? So really, I sort of... So if I might just take a moment to reflect, what I did wrong, apart from not trying to get a closed form, and I kept trying to use recursion to solve my problems. That didn't work out. So lesson learned. We're looking for closed forms. I'm not sure that this is going to work, but I am so much more confident because if 2k divides g of k, then you're going to have those factors there, and that's going to be really nice. What was I saying? Oh, so I was relying on recursion. I was also ignoring sort of the setup they gave me in B part, where they said, here's f of even in terms of an odd and something. And so, that's sort of the subtle hint that look at odds and evens. Look at odds and evens. And I haven't been doing that. So now let's let h of k equal f of 2k plus 1. I still know that h of k plus 1 minus h of k is going to be 2k plus 3 times 2k plus 2 all over 2. Okay, because we did prove, so it wasn't a complete waste, but we did prove this, and I am making extreme use of that. Okay? I like that, and that's a recursion that works regardless of whether or not n is even or odd. But once again, we have a quadratic first difference. So once again, I should be able to get a cubic equation here. So a of k plus 1's cubed. I'm going to change this and do it the same way I did g of k. So that'll be h of k minus h of k minus 1. That's how I did the previous one. And that'll be k plus 1 times 2k all over 2. So that'll be 2k plus 1 times k, or 2k squared plus k instead of the minus k we had before. So and I don't have a problem using the same coefficients. Again, so that'll be a k cubed plus 3ak squared minus 3ak squared plus 3ak minus 1 minus a, sorry. And then bk squared minus 2bk plus b, and then ck minus c, and then d. So we'll just cancel some things out. K squareds, bk's, ck's, and d. And of course we still have plus 2k squared plus k. So we've got 0 is equal to 2 minus 3ak squared again. But it's going to be a little different now. 3a minus 2b plus 1 instead of minus 1. Okay. And then plus negative a plus b minus c. So, and this is different than the last one, right? Yeah, because that was minus 1. 2b minus 1. So that should alter what we get. So once again, a is going to be 2/3. And so 0 is 3a, so 2 minus 2b plus 1. So 3 minus 2b. So b is going to be 3/2. And now we have minus a plus b minus c is equal to 0. So that's 2/3. I'm going to make it 4/6. So minus 4/6 plus 9/6 minus c is 0. So that's 5/6 minus c is equal to 0. C is 5/6. And so h of k should be 4k cubed minus, or say plus 9k squared plus 5k all over 6, and then plus the d value. Now, we know that h of, so for an odd number like k is 0, so h of 0 is f of 1, and we know f of 1 is 0, so this should be fine. And just as a little double check, what's h of 1? H of 1 is 3, and f of 3 is 3. So that should be 4 times 27 minus 81, so that'll be 1 times, so that'll just be 27, plus 5 times 3, so that'll be plus 15. So that'll be 42 over 6, which is 7. Uh-oh. I needed it to be... Oh, no, sorry, this is 1. Oh, silly me. So that'll be 4 plus 9 plus 5, which is 18 all over 6. And I don't know where I got minus 81 from anyway. Doesn't matter. Okay, so this really is h of k. And I can factor this as well. This will be k, and then we'll have 4k plus 1 times k plus 5. No, 4k plus 5 times k plus 1? All over 6. Okay. I think we're good. So, f of n, just a recap, is g of k, which is k times k plus 1 times 4k minus 1 all over 6 if n is equal to 2k. And it's h of k, which is k times k plus 1 times 4k plus 5 all over 6 if n is k plus 1. All right. We have closed forms. I am much happier with this. Now, supposing that n divides fn. Break it into cases. So if n is odd, then I will know the particular form here. Well, let's start with even, actually. So if n is even, then n is equal to 2k. And so we're saying that 2k divides k times k plus 1 times 4k minus 1 all over 6. Okay. So, what has to happen here? Well, then... there is an integer r, so that 2kr is k times k plus 1 times 4k minus 1 all over 6. But that would be 12kr is k times k plus 1 times 4k minus 1. Divide by k on both sides, so we'll get 12r is k plus 1 times 4k minus 1. So I need 12 to divide k plus 1 and 4k minus 1. Is that possible? I feel like it shouldn't be immediately possible because we didn't have any fn's that were multiples of n. Okay. But as long as I can get 12 to divide this, then we're all set. So that means 3 has to divide k plus 1 or 4k minus 1. And actually, one thing to notice, but if 12 divides it, then 4 has to divide it. But 4k minus 1 is automatically odd. And that tells me 4 has to divide k plus 1. Okay, so, it's not impossible so far. So, I guess we could say 12 divides k plus 1. Maybe something like 17 or something would do it. Or if k, maybe if k is 11, so maybe f of 22 would have worked. And I just didn't go up that high. So this is true if and only if 3 divides it. And 4 divides it. So 4k minus 1 is odd. Therefore, 4 has to divide k plus 1. Okay. Yeah. So that's fine. 3 is prime. So 3 divides k plus 1. Or, and possibly both, 3 divides k minus 1. But 3 divides 3k. So that means 3 divides the difference of 4k minus 1 and 3k. So 3 divides k minus 1. So these are exclusive. So 3 can't divide k. And 4 must divide k plus 1. These are our conclusions. Okay, so what can k look like? So k looks like 4s minus 1, but it can't be a multiple of 3. So, what do we want to say? K can be written as 12s plus t, where t is 0, 1, 2, all the way up to 11. All right. Now, if t is 0, 3, 6, or 9, then 3 divides k. So that tells me t is going to be 1, 2, 4, 5, 7, 8, or 10 and 11. All right. If 4 divides k plus 1, then 4 divides t plus 1. So t must be equal to 3 or 7 or 11. But 3 can't be, t can't be 3. I already remarked that, but it can be 7 or 11. Therefore, n looks like 2 times k, which is going to be 24s plus 7, or 24s plus 11. And this is why I didn't have any examples. So n is, another way to say it is, n is congruent to 7 or 11 mod 24. Just to write this down with modular arithmetic. Okay. Oh, no, 14 and 22. My mistake. I forgot to multiply by 2 again. Okay, so that'll be 14, 22. So n is congruent to 14 or 22 mod 24. Fine, fantastic, love it, great. Okay. So that's what happens if n is even. If n is odd, we are really cooking. I'm happy that I chose to take a break and tried to do closed form. So n needs to divide hk, which was k times k plus 1 times 4k plus 5, if I remember correctly. Let's just go back and double check. Okay, so k times k plus 1 times 4k plus 1 over 6. All right, fantastic. This, I feel like, might be a weirder situation, but fine. So, 2k plus 1 needs to divide k times k plus 1 times 4k plus 5 over 6. Therefore, there is an integer r, so that 2k plus 1 times r is k times k plus 1 times 4k plus 5 all over 6. I guess we could then say 12k plus 6 r equals k times k plus 1 times 4k plus 5. This doesn't actually simplify in any way, so don't think that this is particularly helpful. So I know that 1 and 3 work. Is this maybe a situation where these are the only ones that do work? 2k plus 1 needs to divide k plus 1, 4k plus 5. I really, really, really want to write this 4k plus 5 as 2 times 2k plus 1 plus 3 all over 6. So, I can break this guy up into k times k plus 1, 2 times that, 2k plus 1, all over 6, plus 3 times k plus 1, all over 6. Okay. So, what can we do now? So as long as k times k plus 1 over 3 is an integer, this first part will be a multiple of 2k plus 1. And as long as k times k plus 1 over 2 is an integer, which it always is, and is a multiple of 2k plus 1, then again we're all set. But is that the only situation? I don't think so. So There appears to be more to consider. Well, hold on. Let's say 2 times k plus... I'll simplify this to k times k plus 1 all over 3 times 2k plus 1 plus k times k plus 1 all over 2. This is always an integer. Because either k or k plus 1 is even. If k is odd, then k plus 1 is even. If k is even, then k is even. Alright, so we always get an integer here. And so that tells me that this should always be an integer as well. The only question is k times k plus 1 over 3 an integer? So this is going to be 2k plus 1 times some sort of r. Just so I get rid of this divide symbol here. So I don't need to worry about that. So for some integer r. Okay, then 2k plus 1 times r minus k times k plus 1 over 3. So this has got to be equal to k times k plus 1 over 2. Now, what can we do, if anything? So I want to start trying to make assumptions that, k times k plus 1, it has to be a multiple of 3. But I'm trying to think, is there any other way that this would work out? So I know this is an integer. This is an integer. Therefore, k times k plus 1 times 2k plus 1 all over 3 is an integer. Is this already a fact? Surely it must be an integer. Yeah, in fact, it's always a multiple of 2, I think. Because this is the sum of... This is the sum of squares formula. K times k plus 1 times 2k plus 1 all over 6 is the sum of the first k squares. So that's nice and neat. So, that's always an integer. Okay. But my question is, what can we do here? And I'm sure I keep saying that on the video, but I'm getting a bit stuck again. I'm happy with the progress we've made. I know exactly, 14. In fact, I should, if I can, even go back and double check. Because f of 14... Where was my chart? I had a chart of possibilities. I stopped just before 14. What would 14 have been? So from there to there is 66. The next one is 13, so we add 8, and so that 91. So if I add 91 to that, I'll get a 2 there, and a 252. I got a 1 there. 11, bring down the 2. 14 times something is 112. 14 times 8? Yeah, 14 times 8 is 112. Wow. So there we go. That really did work. Still got more to go. There we go. All right, so we're back to where we were, and I did double check that, 14 works. I'll assume 22 works as well. Anyway. Here I'm quite stuck. Not entirely sure where to go with this. Do I want to keep rearranging this formula? So if I move the 2k plus 1 around to the other side, no, I'm not liking the 2k plus 1. Yes, I know it's odd, but I can't see any of its factors. It's not very clear that this is where 2k plus 1s fit in here. Like, I recognize that k and k plus 1 add up to my n, but I'm a little lost. And maybe, I don't know, maybe I shouldn't be focusing on the k value? Because we are interested in n, and I don't know anything about n other than it's 2k plus 1, and it's just, there's not a nice clean factor here. So is there another approach I can make? 2k plus 1 is n, but that also means that k is 2 minus 1n. And so 2k plus 1 has to divide k times k plus 1. I'll stick the 4k back in just for good measure, just because I can't remember specifically what I had on the previous page. But that's the same as saying n minus 1 over 2, n plus 1 over 2, 4n minus 4, it'll be over 2 plus 10 all over 6. But does that help me in any way? Well, n minus 1 and plus 1 over 4. I can divide by 2 there, so 2n plus 3 all over 2 all over 6. I get another 24. That's a plus. And now I'm focusing more specifically on my n. I probably could have done this with n as even as well, but I didn't really need to, actually. Okay, great. So n has to divide that. But then, so I think we're in a slightly better situation. So 24 nr has to be equal to n minus 1 times n plus 1 times 2n plus 3. And so, but there's no factor of n that I can take out, just like there wasn't a 2k plus 1 that I could take out. So, perhaps this isn't the best thing to do either. Yeah. Well, no. So... Oop, dropped my pen. I don't want... was it a mistake bringing the 24 over? I mean, this is, by the way, for some r. For some integer r, but what can we do from... Is there anything we can or should do from here? So here's an n. I suppose if I expand this out, I'm noticing difference of squares here. Yeah, I don't think this is going to go anywhere. Okay. So n divides this side, and n divide. So okay, I can rearrange this. All right, now I'm excited. So I'll bring the 3 over here. 2n cubed plus 3n squared minus 2n minus 24nr. And this is an integer over here. Like, the whole thing is an integer. But it has a factor of n. Haha. So 2n squared plus 3n minus 2 minus 24r, whatever r is. But that tells me that n has to divide 3, so n could be 1 or 3. Both work. Because f at 1 is 0, 1 divides 0, and f at 3 is 3, so 3 divides 3. And this wouldn't have worked. We wouldn't have gotten something similar in the even case. So for a second I had a panic that there was something similar in the even case, but specifically this relationship being plugged in is what got it for me. I wonder if there was a similarly fast way to do it. Well, surely the same rearrangement could work with n is even, but we've got both cases, so n equals 1, 3, or n is congruent to 14 or 22 mod 24. And if you're not comfortable with modular arithmetic, then n looks like 24s plus 14 or 24s plus 22. So that's another way to say that. And that about does it. Now, it's been a long question. I think this might be my longest video, but I think I've said that before with some of the Canadian senior papers, so I'm just going to sort of wrap up and then take a look at how long this was. I'm hoping. I really should write down my start times when I do a question 10. Not important. So if you're still with me, thanks for watching. I'd apologize for fumbling in the middle, but that's kind of the point of these videos, is for me to go through it and talk it out and get stuck from time to time. That happens more often than not on the question 10s or the B3s. But once again, I'd like to remind you, if you just want pure solutions, my videos are not my videos are not where you want to go for that. Waterloo puts out their solutions. Sometimes for a longer question, they put out multiple solutions, if there are multiple ways to do it. I'm going through these as someone who has done a lot of these contests and is trying to just talk my way through it, think my way through it, and share that thought process with you, so that you can understand the mind of a champion. So, you can just understand someone who has experience with this stuff, has gone somewhat far with this, and maybe you can learn a thing or two. And if the thing you learn from this long video is just stay away from question 10s, then I do apologize. Question 10s aren't always that bad, but as you can see, sometimes you just get stuck. Although, once I stopped trying to just focus purely on the recursive formulas, and instead used that one recursive relationship, f of n is f of n minus 2 plus n times n minus 1 all over 2, to get closed forms, it actually didn't take me that long. And, there's sort of a catch when you do 8, 9, and 10 is, do you see it or do you not? This year, didn't see it. I wouldn't have been done in time. Even, so there's, eventually I saw it, but no way would that have been good in terms of contest time, because you got to factor in me doing all the other questions. But maybe next year it will be something I latch onto, and maybe this year for the contest it'll be something you latch onto, or maybe not. There's always that risk, but you never find out until you try question 10 or 9 or 5 if you're a beginner or something like that. So you got to try them, and you got to practice these contests to see these sorts of things. So thank you for watching. I will see you if you're looking for another Euclid. I have 2007 and earlier. Up next will be 2009, but not for some time, because I'm going to go back to doing some Gauss papers, because I try and do all the Waterloo contests. Thank you guys for watching. If you're looking for more written questions, of course, you can do Freyr, Galois, and Hypatia, or the Canadian Intermediate and Senior papers as well. Take a look at those. Thanks for watching. I'll see you next time.